Swayam Prabha. Digital India. Educated India.
Okay, welcome back, and we are almost towards the end of the discussion of the laminar diffusion flame, laminar non-premixed flame, and one of the issue that occurs in the laminar diffusion flame is the soot formation when you burn hydrocarbon fuel, and that is what we are discussing. So, this is where we stopped, and we will continue from here. So, we looked at this particular example of a simple burner. These are the dimensions of that particular burner: tube diameter, fuel flow rate, nozzle, and this is a visible flame height. Now, and the fuel is C2H4. And this is an fuel is coming through this nozzle or the tube, and this is where air comes in. So, this is fuel which will try to go like this will be air which will try to enter in, and the reaction will take place along the stoichiometric situation. Now, then this area where you see this aromatic structure formation or ring formation. So, this is as happening at the where the this hydrocarbon fuels, this C2H4 gets into this higher order hydrocarbons and forms this sheet like structure or ring like structure. Then at this position of the flame, the other process which actually takes place, that means from here to here within this visible flame height, from this sheet like structure there is a phase change takes place. So, you get the start getting the small size particle, and these small size particles when they grow there is a surface growth and coagulation. So, this is the situation where, and the rest of the height which is a sort of your total flame height or flame envelope, there the oxidation takes place. If the oxidation is quite complete, then you do not get to see these particles at the end of your process, otherwise you get to see these particles. Now, this is where there are some images. These are the primary diameter, particle diameter, this is height above the burner, and there is a variation of the fuel flow rate, and you can see how it varies. So, up to certain height there is not much change which is visible with the change in the flow rate, and that because up to that this is the process which takes place, or rather this process. Then beyond that there is a oxidation process which is quite different from different flow rate, and that is why that happens. So, these are the typical images of the soot what one can see under microscopes. This is what visibly one can see there. So, there are, just to give you an idea, even there are a lot of computational effort has gone into prediction of soot and all these things. There are different models. Say one lifted ethylene air flame, but this is experimentally observed soot volume fraction, and this is how one can computationally obtain. And so, this is another area which requires lot of attention, especially under turbulent condition where you get soot and all these things. How accurately one can model, because most of the natural processes, I mean reacting system, they are sort of directly or indirectly burning hydrocarbon fuels, and once you burn hydrocarbon fuels under non-premixed mode, these are bound to happen. So, accurate predictions of the shoot is an important aspect and quite challenging. There are algebraic models available, there are advanced particle based models available, but none of them are accurate enough to give you these things. Now, that is pretty much concludes the discussion on the laminar non-premixed flame. Now, we will discuss some other topics, and before moving ahead with the turbulence or turbulent flow discussion. So, one of the things that I would like to discuss is this combustion engine, because one must have some idea about these combustion engines. So, the practical systems, pretty much what you look at it, the practical system, there are two type of combustion engines, one could be internal, another could be external. Now, most of the system practically that we see, they are internal combustion engines, which is primarily used or dominantly used for propulsion system. Whether you think about application of the gas turbine, or whether you think about the application of the automobile engine, and the external combustion engines also will look at it, and the working principle of internal and external are quite different, especially there is a difference in the nature of the working fluid. So, that makes them quite different from these things. Now, if we think about the working fluid for internal combustion system, so here internal engines produces work by pushing a piston or turbine blade that in turn rotates a shaft. So, any internal combustion unit that produces that work by pushing a piston or doing that. Now, it works at high momentum fluid that is used directly to the propulsive force, and especially in the internal combustion system, the energy source is the combustible mixture. So, the energy source is the combustible mixture, and the combustion products is the essentially the working fluid. And rather in a external system or external combustion engine, the combustion products are used to heat a second fluid that acts as an working fluid. So, here the combustion products is used to heat a second fluid that acts as working fluid. Okay. So, that is the basic difference. Now, the most common internal combustion engine is the gas turbine engine, then you have, one can write this internal combustion system which are gasoline engine, which is you can spark ignition engines, homogeneous stratified start engine, diesel engine which is used in your heavy road vehicles, then HCCI engine which are homogeneous charge compression ignition, this is obviously under development stage, and optimize gas turbine engine, whether it is used for aircraft propulsion or stationary power plant, then rockets engine or chemical rockets. So, these are what they use internal. Now the external combustion engine, you can think about steam power plant, then home heating furnace, by gas or oil, Stirling engine, now there are some more engines which we do not categorize them either internal or external. For example, solar power plant, then nuclear power plant, fuel cell, electric rocket propulsion. So, this we do not specifically categorize or put them in the either of these basket, like internal combustion or external combustion engines. Okay. Now, one can also, now for the internal combustion engine, you can have one category could be steady flow engine, which brings gas turbine engine, ramjet or scramjet engine, chemical rockets, or another category could be non-steady flow. So, where you can have non-premixed charge, premixed charge, stratified charge. So, if you draw a nice picture of this, so one is that your all is your internal system. So, either one can have steady, so that could be one category. Under steady you have gas turbine, then you have ramjet or scramjet, or you could have chemical rockets. Now, here also you can have turbojet, you can have turbofan or turboprop, you can have turbo shaft. So, here turbojet, what it does, that all jet except for work needed to drive compressor. Now, in turbofan or turboprop, part jet, part shaft work to drive a fan or propeller. turbo shaft, all shaft work to drive the propeller, generator or rotor. Here there is no compressor or turbine. It uses high Mach number ram effect for compression. Chemical rockets, there could be again two types, one is solid, another could be liquid fuel. Solid fuel, fuel and oxidant are premixed and placed in chamber, whether in the liquid case fuel and oxidant are pumped separately to mix in the chamber. Now, unsteady case, so you have a premixed charge. So, under premixed charge you could have two types, either gasoline or gas engine or HCCI. Now, gasoline, it is a homogeneous charge spark ignition engine, and this is homogeneous charge compression ignition engine. So, there is a difference, small difference. Then non-premixed charged, and stratified charge. So, in this case non-premixed charge, only air is compressed, fuel is injected into the cylinder, compression ignition system like a diesel engine, and this case stratified partially premixed charge, equivalent ratio changes spatially. So, there is a nice differences among all these different engines. Now, we look at the gas turbine engine. So, there are where you have turbojet, then you have turbofan, then you have turboprop, then turbo shaft. So, here in the turbojet, what it does is that all jet except for work needed for the turbine that drives the compressor. So, it is a turbojet. Now, in the turbofan, there is partly jet and part shaft work to drive the fan, obviously in addition to the compressor, and that fan provides 5 to 6 times more air passing around the engine core. Then you have turboprop, where it is pretty much similar to turbofan engine, but the rate of airflow through the propeller may be 25 to 30 times the airflow through the core engine. So, that produces the primarily the force. And the turbo shaft, this is an industrial stationary engine used for power production. So, this is used in power production to drive a pump. Sometimes it is also used in helicopter to drive a rotor or drive a ship's propeller. Now, all these different engine, they have one thing which is common, is the gas generator. So, there is a basic gas generator one can think about. This is a compressor, then there is a shaft connected with turbine, then this is what it comes and goes out. This is your sort of burner, you have fuel inlet, goes in, this is hot high pressure gas, this is your air inlet. This is a simple schematic of a basic gas generator. Now, top of that one can actually build up the turbojet system, where we have compressor which is connected with a turbine. Now, this is connected with the burner where fuel goes in. This is your burner, and this guy comes and goes through some exhaust nozzle. This is the hot gas. So, then finally, we get high speed exhaust gas. This is a schematic of a turbojet system. So, similarly, you can see the turboshaft engine or turboprop engine or turbofan engine. So, the one can draw that schematic. There is a fan sitting there which is connected with a compressor which is connected with a shaft turbine. There is this is your burner, fuel comes in, this is air. So, this also fan, this is moderate speed gas, this is cold flow. Then finally, it passes through a nozzle and you get the exhaust. So, this is hot flow. So, this is your schematic of turbo fan, and at the same time turboprop will look slightly different. There is a gear which is connected to the compressor, shaft connected to the turbine, and in between you have the gas generator which has fuel is burner. This is propeller, this is low speed air. Here is the air inlet, and finally it passes through the nozzle to hot gas. So, that is your turbo prop. Now, already we have seen some images of turbofan engine while in the introduction lecture. Typically, that is used in your aircraft engine. There is a big. Now, there is also a trend of pressure ratio. If we plot, they started with somewhere 1940, then 50, 60, 70, 80, 90, 2000, 10, and this way if it is goes 10, 20, 30, 40, 50. So, there is a increasing trend of increasing pressure ratio. This is overall pressure ratio, and this is years. So, these engines are, both our civilian aircraft and fighter aircraft, they use sort of a turbofan engine, but the different category. There is a one thing that, like in your turbofan, there is a portion of the air which goes out of the core. This portion of the air comes through the core of the engine. There is a call, this ratio, if this is the cold flow and this is the hot air, the ratio is the bypass ratio, that the percentage of the cold flow of the total. Now, typically in the civilian aircraft, the turbofan engines are high bypass ratio engine. So, there the major component of the thrust generated from this cold flow, whereas if you look at the fighter aircraft, they are the low bypass ratio engine, where the primary air goes through the core of the engine. So, most of the thrust is generated in the core of the engine. Now, we are talking about the combustor. Now, these combustors are also of different natures. There could be like this kind of situation where you have a which is connected. So, this is called, or some schematic of a can combustor, or you can have something like which is called turbo annular, or one can have some simple, this is an annular combustor. So, there also the development has been made, they try to mix this can annular kind of combustor, and that has some advantages, some disadvantage, but this is what has been tried by the different people to see. And if you go to internet and try to search for these different kind of combustor, and there is also one can use multi cans combustor, can annular combustor. So, these things you can find out in the Google, and there are, or rather one can look at the book of the gas turbine engine, specifically different kind of combustor and what you use for the aviation purpose or in the aircraft or engine, and what you use for the gas turbine in the land based power plant production, they are different, but one can have a look and see what kind of combustor they are using and what not. So, we stop the discussion today and continue from here in the next lecture. Thank you.